Hello, class. Today we'll see the topic of ADC interfacing, that is your Unit 5 as per your syllabus. So, we'll see. Before that, let's first understand what is the objective to read this topic or to understand this topic. With this topic, the objective is to build and test a microcontroller based system, because in a physical world or in a physical practical applications, we have many different um, physical quantities that need to be interfaced or that need to be controlled. So for that you need we as a programmer need to build and test a microcontroller based system. So that is our first objective. Second, since those physical quantities will be in some different form, and we as an engineer, we have to convert it into um an understandable quantity. Like if suppose you have any electrical quantity, that will be in terms of voltage or current, but we understand the physical quantity. Like if you want to sense a temperature, if you want to measure pressure, if you want to measure flow, these are the quantities which are non-electrical one. But we as an electrical engineer will first sense it as an electrical quantity and will then convert it into its original value. Okay, so for that we need a converter which will be an analog to digital. So that means it will convert that variable analog quantity into a digital one, which can be easily understood by any person. Even a non-technical person can understand that value. Okay, at the end, the objective to go through this topic is, first of all, we have to understand the concepts and techniques that are required to interface these devices. Okay, interface this analog to digital converter with your computer or with your microcontroller, and have a software, embedded software for this purpose. So before we go with the interfacing part or the programming part, we first of all need to understand the concept. So that is the objective for this course. First, build and test a microcontroller based system. Second, interface the system to the AD converter. And finally, understand the concepts and techniques that are required in designing that interface systems. Okay. And of course, at the end of this session, as we proceed, I am sure that we'll understand how to build and test a microcontroller based system, and finally how to interface the system to the analog to digital converter. So this is what is expected to be achieved till the end of the session. So we'll proceed. We'll see next. So when you're talking about analog to digital converter, first of all, understand what is analog and digital. I am sure that you know it. What is analog? Analog is basically an variable quantity. Variable quantity. It can be either a voltage or current, and it converts to a digital value. It converts it into a digital number. Okay, digital number can be any value, but that value is represented in the form of zeros and ones. Okay, so that is the analog to digital converter. It would accept an analog input, which might be a voltage or a current, and it will convert it into a digital value, its equivalent digital value, but that value will be represented in the form of zeros and ones. Some ADCs that are available in market are 0803, 0804, 0808. These are just the numbers provided by the manufacturer. As per your syllabus, the ADC which will mainly focus for this lecture is your 0808 or 0809. So it's an 8-bit ADC. It has a resolution of 8 bits. We'll see what do you mean by resolution. It requires a supply of 5 volt DC, and it takes a conversion time of 100 microseconds. What do you mean by conversion time? Obviously, conversion time means the time required by this ADC converter to convert a signal from analog to digital. So the minimum time it takes is the 100 microsecond. So now, before you select the ADC, the most important factor that you should look at is the resolution. So what do you mean by resolution or a step size? Step size, it is the smallest change that can be sensed by the ADC. So when you select the ADC, obviously we are selecting it to convert that analog value into a digital one. So that analog value can be anything, like Suppose you have to sense a temperature and you want to display it at some LCD or LED that way. So temperature is an physical quantity. You'll obviously use a transducer to convert it into an electrical signal. That electrical signal will be either voltage or current. That analog voltage or current will be sensed by this ADC and will be converted into a digital value, and that way you will get your temperature. Clear? Right. So but then, if suppose there is a temperature change of a very finite value, let's suppose that at this moment temperature is 25 degrees Celsius, and after a certain period the temperature is changed only by 0.01 degrees Celsius. So that's a very negligible amount of change in temperature. But still, for my application, even if there is a small change in the temperature, I want my system to identify it. So that is called as your resolution. The smallest change, even if it is there, that should be identified by the machine. So that is my resolution. So when you're talking about a ADC, you always have to first ask yourself, what is the resolution required for my application? So that is your resolution. Mathematically, it is calculated as plus V reference minus V reference by 256. Why 256? Because 256 defines the word length of the ADC. So for this, I have considered as an example that your ADC is 8-bit. So obviously you calculated it as 2 to the power 8. If suppose your ADC is 4-bit, so obviously the factor over here would be 16, 2 to the power 4, right? So that way. So always remember that more the word length, more precise will be the resolution. Shorter the word length, not much resolution can be achieved by that ADC. Clear? So that is your resolution. So see here, I have given you an example that I have considered an ADC of 8-bit, provided a V reference voltage of 5 volt and minus as the 0, that is ground. So by that formula we have calculated resolution. It is coming out up to 19.5 millivolt. So what does this means, resolution 19.5 millivolt means what? That this is the smallest change that can be sensed by that ADC. If suppose there is a change in some temperature which gives you an output voltage of, let's suppose, 10 millivolt. So will that ADC identify that change? No. Yes, of course. No, it won't not identify that small change because that particular ADC has a resolution of 19.5 millivolt. Means below that, if any change occurs, then that ADC will not identify that change. So that matters to you. If you want to understand or identify the smallest change that can be of around 1 millivolt, so accordingly you define your ADC. Clear? So if suppose I have selected this ADC which has a resolution of 19.5 millivolt, but I want my ADC to be more precise. I want it to sense even a 10 millivolt of change. So then what can we do? First thing, you increase the bit size. 256 for 8-bit, the word length is 256. If suppose I go for a ADC which is 16-bit, so your word length obviously gets increased, so your resolution will get improved. Yes, right. But then if suppose my ADC is fixed, it's 8-bit ADC, now I cannot change my ADC, then you can play with the reference voltage. Change your reference voltage or reduce the reference voltage. Earlier we have used your voltage as 5 volt, so with 5 volt we got it as 19.5 millivolt. So go on, reduce your V reference voltage. Let's suppose we selected it 2.5. So the minimum change we can observe is 9.7 millivolt. Okay, so obviously 19.5 millivolt, 9.7 millivolt is the smallest one. So we are near to the 10 millivolt. Clear? So either you increase the word width, that is the size of your ADC. Either you go from 8-bit to 16-bit or to 32-bit or to 64-bit according to your requirement, or you decrease the reference voltage. So that way you can improve your resolution. So before selecting ADC for a particular application, first of all, identify the resolution required. Now, so this is your ADC 0809. It's a 28 pin IC. See, it's a 28 pin IC. You have here 8 input channels, IN0 to IN7. Then you have 8 output channels, that is output 1 to output 8. So this input channel, this defines your analog input, and this is your digital output. So when you're using an ADC to convert analog input to output, so you will connect here 8 different sensors, let's suppose. So you can have 8 different sensors connected to this ADC at a time, but always remember there's only one output bit, right? One set of output bits, 8 bits are provided. So that means one channel will be processed at a time. Even though you can connect 8 channels at a time, but processing will be done one at a time. So whichever sensor you are connected at IN0, that let's suppose that is first processed, so you will get a digital equivalent of that value onto the output, if and then IN1, then IN2, that way it will proceed. So who decides which channel has to be selected? That is being decided by these 3 pins. These are your address pins, address A, B and C. These 3 pins decide which channel is selected. So then you have a separate combination. 000 will give you input channel 0, then you have 100. So that will help you to select channel 1. So that way you can select, with these 3 bits will help you to select any one of these channels. And then you have ALE, that is address latch enable, for latching the address pins. Then you have V reference plus, V reference minus, which I have discussed in the last slide. You can connect this reference voltage. Normally V reference is all minus is connected to ground, and we always connect a plus V reference to it. Now it requires its own voltage, so that is your VCC. It requires a 5 volt of supply voltage for operation, so that is connected there. Then you have a ground pin. This IC is grounded. Then this IC requires its own clock pulse also to operate. So this clock pulse can be provided by the external clock source, or you can provide this clock from the microcontroller itself. Now microcontroller has a clock frequency of 11.059 megahertz, which is very big value for this ADC. But this ADC does not require that much of clock frequency, so you can reduce that value by using flip-flops. So that way you can connect it to clock. Then you have start. The start is basically start of conversion. So we sometimes call it as SOC also. So when ADC selects one channel and starts processing it, then this SOC has to be given a signal from a low to high pulse. When a low to high pulse is given to this start pin, then this ADC starts converging the analog input to the digital output. And once it completes its conversion, that means the analog value is converted into output, then it gives a high to low signal to this EOC pin. EOC stands for end of conversion. A high to low. When this pin gets low, then it gets to identify that the microcontroller will get to know that conversion process has been completed. So when this goes high to low, microcontroller will get to know that conversion has been done. Then microcontroller will give a low to high pulse to this output enable pin. Okay, OE stands for output enable. When this pin gets a low to high pulse, then it will send this digital output data to the microcontroller. Is that clear? Okay, once again we'll revise it. First, connect your analog sensors to this channel. With the help of these 3 address lines, with the combination of these 3 address lines, select which channel has to be processed first. Suppose we have selected channel 0. That channel 0 will be taken in. Now, to start off the conversion process, you have to give a low to high pulse to the start of conversion pin. This is given by the microcontroller. Then it will start conversion process. Once the conversion process is completed, this ADC will give a high to low pulse to this EOC pin, which will be sent to the microcontroller. Microcontroller will get to know that conversion has been completed. Microcontroller will give a low to high pulse to output enable pin. Once this gets output enable as low to high, then ADC will send this converted digital data to the microcontroller. Clear? This is the step it follows. And in the same way, we have to write down the program. Okay. So now, see, this is the table, or this is the combination with which you can select the channel. When add C, add B and A. See, remember it is written in reverse order. It's A, B and then C. Or you name it as C, B and A. So it's 000 will give you channel 1, 010 will give you channel 2, that way. This I think you can remember easily, but don't get confused with this. Normally we have a habit of writing it A, B and C, but this is written as C, B and A. Okay. After this, we'll see how block diagram, how any ADC would work. So this is the block diagram. It consists of a address latch and decoder circuitry. It mainly has these three pins. These are your address pins, address C, B and A, and you have an address latch enable pin. This always has to make high, then only it will latch the address lines with the channel. Combination of these three lines, address C, B, A, will decide which channel is selected, right? Then you have a channel multiplexing analog switches. Here you can have 8 analog inputs at a time, but with the help of this multiplexing you can select one channel at a time. So that one channel is selected, it is then given to an ADC. This is the block of ADC. Here you have a comparator. Then you have a successive approximation register, SAR. It stands for SAR, successive approximation register. So here you actually have one internal DAC converter. So you have a switched tree, then you have a 256 resistor ladder. So how basically it operates: when you receive an analog signal, the comparator will provide it to the successive approximation register. It basically works on the technique of successive approximation. That is why this is named as SAR, successive approximation register. So what is that successive approximation? It is basically you get an input voltage. It will get converted into a digital value one by one. Like this register is an 8-bit register. It starts with setting the MSB bit as high. Will calculate the voltage, that digital value. That digital value is then converted into analog one. That analog is sent to again to the comparator, and this value is compared with the input, analog input. And comparing those two values, this SAR will decide whether to keep that bit or to drop that bit. This way this register will follow 8 iterations. 8 times it will follow this loop. Okay. So once it is done, then it will inform through the end of conversion signal, that is conversion has been done. Then microcontroller will give you output enable pin, and then data will be sent to the microcontroller. So don't worry if you did not understand this successive approximation, we'll discuss it. See, here I have given you the theoretical description of that block diagram. First is your 8-channel multiplexer. You can accept 8 analog inputs in the range of 0 to 5 volt because your ADC is 5 volt. So you can go with that. Then you have a comparator. Comparator converts the DC input signal into an analog AC signal and then amplifies it to the AC signal. Then you have a 256 resistor ladder. It is provided, which guarantees that no digital codes should get missed. That is again a digital to analog conversion process. Then you have successive approximation register. It performs the 8 iterations to determine the digital code. So let's see how that basically works. So here I have considered the same example, that 8-bit ADC, which we have calculated in the second slide. I think we have calculated. So this was the resolution we got, 8-bit ADC with 5 volt reference voltage. So 19.5 millivolt was the resolution we have achieved. So let's suppose we have connected analog input to channel 0 and that input voltage is 3 volt. So how that successive approximation register will calculate that this value is 3 volt? How it will do? It will start performing 8 iterations. Okay, it's a 8-bit register. See, so since it has the lowest resolution or the smallest change that it can identify is 19.5 millivolt, so your bit D0 will be 19.5 millivolt. It is written in volt, so 0.0195 volt. Then you have D1. D1 is 2 to the power 1. So it's 0.0195 into 2 will give you 0.039. Then here you have 2 to the power 2. So 4 into 0.0195 will give you this value. Then 2 to the power 3, that is 8. 8 into 0.0195. So that way. Then 16, 32, 64, 128. Multiplied by the slowest resolution, you can identify this value. Clear? You can calculate these values. So now these are the values which have been there. So now how the SAR will start working? It will start working by making the MSB bit high, keeping rest of the bits low. So when this bit is high, that means what is the voltage value? It is 2.5. So see here, what is your output voltage? It is 2.5. So see, when I say output voltage, that I am saying this value, output voltage, and this is your V in. This is 3 volt. We have got an analog input, and this SAR now started with keeping MSB bit 1. It has done the calculation. You have achieved a value 2.5, converted into digital, then digital to analog, and it is given here. Now this 3 volt and 2.5 will be compared. Okay, so now here 2.5 volt you have achieved. Now in the comparator, these two values will be compared. So what it will do, if V in is greater than this VO, then it will pick this bit, otherwise it will drop. So now this 2.5 is less than this 3 volt, that means 3 volt is greater, V in is greater than VO, so it will pick that bit. Okay, pick means what? In the next iteration, this bit will remain as it is. So it is 1, carry forwarded. Then next iteration, it will make the next bit high. So now summation of these two, 2.5 plus 1.25 will give you 3.75. Now see, this 3.75, V in is greater than this VO. No, V in is less than VO. So it has to drop. So this bit gets dropped. This bit means this bit gets dropped. So in next instruction, this is carried, but this bit gets dropped. So it becomes 0. And in the sixth, the next bit gets 1. That way, again the calculation 3.124, it is also greater than 3. So this bit also gets dropped. Then in the next iteration, this bit gets raised. That way it is get calculated. Now it is 2.812, so it has to pick. So in next instruction, it remains same. Then next bit raised high, again calculate summation. It is also less than 3, so it remains there. So that way it is followed, and finally when 8 iterations are done, so what is the number you've got? 1001, 1001. Okay, so this is your 8-bit digital data you have received at the output, 8-bit outputs. Clear? Okay. So this is how your ADC basically works. So now interfacing this ADC with 8051. So I have explained you the process. So similarly, in that way only it is interface. See, first of all, we want to select which channel is being utilized. So now see here is we have connected the sensor at the input 1 channel. So we have to first of all finalize which input pin is to be selected. So that is done through the address ABC lines. So we need to provide the which for 1 it is 001. So for that obviously we would require ports from the 8051. So we have selected any port you can select. There is no such restriction that port 2 only can be selected or port 1 can be only selected. Any port. Only remember that you have to provide data at 001 this way to select channel 1. So for that, one port is selected. Then you have to make address latch enable pin. So you will require one pin for that. Then address latch enable is done. So your channel will be selected. Then to enable the start of conversion, you have to provide a low to high pulse. So again you need one bit which will send data to the SOC to start of conversion process. Once the process is completed, that is conversion is done, ADC will send a end of conversion signal. So here it is written INTR, it is interrupt. Okay, so kind of it can be renamed as interrupt also, or it can be named as EOC, end of conversion. So ADC will send a signal to the microcontroller. So you need one port pin which will act as an input pin. Okay, so you will receive end of conversion. Once end of conversion is known to the microcontroller, now microcontroller has to send a low to high signal to the ADC to output enable. Once ADC receives this output enable, then it will send the data. So it requires 7 bits again, which will accept data. So you require port pins which will receive data. Clear? So from this you can identify that there are few pins which are acting as an input, which few are acting as an output. So P10 to P17 is acting as an input, P2.7 is acting as an input, right? And rest of the pins are your output pins. P2.5 it has to provide output, P2.6 it has to provide output to the start of conversion, P2.4 it has to provide output as to the ALE for address latch enable. Then P20 to P22 it also has to provide data to the ABC for the channel selection. So this is the simplest interfacing of ADC. See here, intentionally I have not shown any clock pulse. You can here simply return external source, because to connect it through 8051 then the diagram becomes a bit complicated. You will have to connect 3 to 4 flip-flops which will provide you the reduced clock which can be given to the ADC. But then that becomes a complicated, so that's why I have not shown it. Here you can directly write it as external clock that way. So see here I have provided you the steps. As ADC requires the clock, it can be provided by crystal or microcontroller or separate crystal. First of all, you have to give a low to high to ALE, which will enable the latch in the address. Then select the channel by these pins, add A, add B, add C. Then give a low to high signal to start of conversion. Remember this pin now, because in exam they might ask you a question to explain SOC pins or EOC pins or ALE pin. So at that time you have to remember this. ALE pin means low to high, start of conversion means low to high. When you give a low to high signal, then only it will start conversion. When you EOC pin always goes low when the conversion process is completed. So it is a high to low pin. Then output enable is also in high to low pin. This is the steps is followed, and same will follow in while writing down the program. So here the question is, write a program to receive digital data from ADC. So here same diagram I have considered. For this same diagram we'll write down the program. So first of all you have to define which port is acting as an input. Port 1. So define port 1 as an acting as an input. Sorry, here we have to write it hash 0FFH. That part is missing. So write it as hash 0FFH. So we have defined port 1 as an input pin. Then select channel. For channel selecting those channel, you have to provide add A, add B, add C. Right? So we require 0, 0, 1. So that means only A pin will have a 1. So that is P2.2. So we have provided 1, 0, 0 that way. So selected channel 1. Why? Because in the diagram we have connected sensor to the channel 1. Then give output enable high to low. So first of all we have make it high. Low will make it when the conversion process is done. Then address latch enable, it has to give a low to high. So provided low to high, P2.4. P2.4 is connected to address latch enable. Then for start of conversion you have to provide low to high. So again provided low means clear, high means set. That way you have done. Once you've done it high, conversion process started. Now what we have to do, we have to only wait and monitor if the conversion process is done. And for that we have an instruction jump if bit. Jump if bit means till this bit P2.7 is high, it has to jump here only. That means it has to monitor. Once this bit gets 0, that means low, then it has to make output enable low. We have already made it high, kept it high, so now you have to make it low. So make output enable low. That means this 8051 microcontroller will send a low signal to the ADC. Once you sent it output low, output enable as low to the ADC, ADC now will, microcontroller will now receive the data at the port 1. Now you simply have to move that port 1 data into some register, and after that, whatever your application is, you can again rewrite, increase the program. If you have to display it to LCD, then write down the program of LCD, or that way. But right now they have asked only to receive digital data from ADC, so we have received the digital data into the accumulator. Short jump and end the program. This was the simplest program. Okay, so even from exam point of view, if they ask you to write the program to receive digital data, this much can be sufficient. No need to go for the LCD interfacing. That again is a different part. Okay, so the simple one. Just go through it once again. Any doubts, you can contact me at any time. Okay, study well, prepare well. All the best.